same, very, very similar to the search, because we simply want to find, if we want to insert an element, then we simply will try to find where the element is. Certainly it is not there. We are now to insert it. But we are trying to find it, and the place where we cannot find it is the place where it should be, so that's the place where we are going to insert it. For example, if we want to insert 14 here, then we are trying to find the place where it should be. It is less than 28, it is more than 12, it is less than 21, no one's here. That means that we are going to link it to this place. Very simple. That means that new vertices are always inserted as leaves. We also say that binary search tree is always built up at its leaf level. All right. What else? If you remember, among the basic operations on data structures, we have this minimum and maximum. How can we find the minimal element? Where is the minimal element? Which is the minimal element? Yes, the very left one, the leftmost one. Exactly. So that means it's very simple. We just begin from or with the root. We are stepping to the left, and because or when we cannot step to the left anymore, then we have found it. That's it. And the same works for the maximum element. There we have to step to the right. Always, and when we cannot step more or make more steps to the right, then we have found the maximum element. The serial codes are again very, very simple. So this is now the root, or it stores the address of the root. And while the left pointer of the root does not equal nil, we update this pointer to the left child's pointer. At the end, this while loop will exit when this pointer gets yes, this one. So there is no more left child, then the tree will just point at the leftmost. And the same works for the maximum, except for we are using the right pointers instead. Okay, and again, the time complexity of the operation. Note that we just, by finding the minimum and the maximum, we just move in one direction vertically in this binary search tree. So the number of steps, the maximum steps, is again or depends again on just on the height of depth. Sorry, on the depth of the binary search tree. Successor of an element. Do you remember what successor means? We had something. The predecessor, the successor is the next element, correct? Nearly the same, yeah. That's very similar. Yes, the next element, but how? Due to their order. So that means that if you remember, if we have elements like 5, 8, 13, 29, then the successor of 8 is 13. But still, if we have these elements in another order, the successor of 8 is still 13, not 29. So successor means that successor is the minimal element among those which are greater than 8. Because if we have them in an ascending order, then all the elements to the left of it are less than it is in an ascending order, and all of the elements which are greater than this 8 are to the right of it. And among those which are greater than this given actual element, the successor is the least one, the minimum. So that this is successor. And from the other side, this is the predecessor. Now, we have elements here somehow in a very weird order, because this is a search tree or what. And we want to find the successor of an element. It is not that easy. certainly we have to know, the first thing we have to know, or what we have to think about is where the elements greater than a certain element are. Because that's the set, the subset of all the numbers, all the elements, where we have to find the minimum. Where, for example, if we want to find the successor of 12, we know that all the elements which are greater than 12 are either here in its right subtree or in the subtree of which 12 is in its left subtree. So here are greater elements and here are greater elements than 12. But we are now trying to find the minimal among those. And because all these elements are in the left subtree of these elements, that means that these elements are less than these ones. So if we are trying to find the minimal, then we have to look for it here. Namely, the minimal element here. But the minimal element is the leftmost. We have just seen. So that means that the tree minimum will find it for us, and it will be 14. And in fact, 14 is the tree successor of 12, or is the successor of 12 in this binary search. But if an element has no right child, what can we do then? We can say that the minimal element in its right subtree, but there is no right subtree. Then we have to lean on the previous observation that greater elements than 26 are in the subtree of which 26 is in its left subtree. 26 is in the left subtree of this one and this. So we have to find the first one here, of which 26 is in its left subtree, and it's easier to find this element as we can think about, because when we step upwards, and because we have links upwards as well, you remember we have parent links as well. So if we step upwards, then we just have to check what the relation between the parent and the child is. If it is a parent-right-child relation, then we haven't found it. So we just step upwards until we find a parent-left-child relation. And at that point, the parent will be the successor. That's it.